curve components themselves. Part of the curve is the intersection angle. The intersection angle is actually designed when you lay out the alignments for the curve, and it is basically the angle between, at the PI, between the back tangent and the forward tangent. The length is, of course, just the arc distance or the arc length of the curve from the PC point of curvature to the point of tangency. Oops. The radius is just the radius of that circular curve. The tangent is distance from the PI to the PC or from the PI to the PT. The long chord is the distance from the PC to the PT. It's the chord of the circular arc. The external is the distance from the middle of the curve to the PI. And the middle ordinate is the distance from the middle of the curve to the middle of the long chord. And degree of curvature is defined by how many degrees there are in 100 foot of arc length or chord length, depending on whether we're talking about an arc definition of a curve or a chord definition of a curve. Typically, arc definition is used for highway alignments, chord definition is used for railroad alignments. Typically, the curve is defined by the intersection angle and the radius. The intersection angle is defined by the layouts of the tangents, as I pointed out before. R is defined by safety concerns and design speeds for vehicles. However, it should be pointed out that you can define a curve by any two of the components that we looked at. So any two of these previous components that we had on the previous slide could be used actually to define this curve. But typically, it's the intersection angle and the radius. Sometimes it will be defined by the intersection angle and the degree of curvature. So let's look at an example and compute the components for this curve. In this example, we've got an intersection angle of 8 degrees, 24 minutes. The PI is at 64 plus 27.46. The minimum radius of the curve is given by 2,864.79 feet, arc definition. And what I need to do is compute all the components of the curve, including the PC and PT. So here's my given. I've got three things given: the stationing of the PI, and the intersection angle, and the radius. What I want to find is the length of the curve, the tangent lengths, the long chord length, the external and middle ordinate lengths, PC, and the PT. So let's look at the geometry here. For the length of the curve, we have the basic geometrical relationship that the arc distance of a curve is equal to r times theta, where theta is in radians. Well, r we have is the radius of our curve. S is going to be the length of the curve, and we know the intersection angle is in fact I. And so basically the intersection angle has to be converted to radians, so our length is going to be r times I, where I is in radians. Now we substitute in our values for the radius and for the intersection angle, and then remember to convert your intersection angle into radians. After you do that, you find out the length of the curve is 420 feet. So the length of our curve here is 420 feet. For the tangent length, what we do is we look at the right triangle OPI PC. If you look at this curve, the tangent is the opposite side of the intersection angle, and we've bisected the intersection angle, and so therefore we're looking at half of the intersection angle down here. We know the radius of the curve, we know the intersection angle of the curve. This is the opposite side, so we've got the opposite and adjacent side, so we use the tangent function. So the tangent of I over 2 is equal to T over R. Now we just have to solve this for T. So T equals R times the tangent of I over 2. Substituting in our values, we find that T is equal to 210.38 feet. If we go to the next one, we can look at our stationing. Now that we have the tangent distance, we can look at our stationing. From the PI, we simply subtract off the tangent distance and we get our PC. And so our PC is 62 plus 17.08. Also from the PI, we could add on the tangent distance. This would be the design when it was actually laid out, the tangents were laid out, this would actually have a stationing already here at the PT. But we're not going to look at that one. We're going to look at what happens to the stationing as we follow the curve. As we follow the curve, we have to add the length of the curve on, and we get that the PT back, which is basically the stationing looking back from the curve back, is 66 plus 37.08. However, as I said before, we can also get the tangent PT, the stationing on the PT, by going along the tangent, which would have been the original design. That is called the PT ahead. And so if we add on the tangent distance to the PI, we get the tangent ahead of 66 plus 37.84. And you can see following the tangents, obviously, we're going to have this longer distance. And so we have a slightly longer distance here. It's not greatly longer, but it's two different stationings. So when you put these two together, the PT back equals the PT ahead. This is called a station equation, and that forms your station equation. Now the long chord is the distance across from PC to PT. Well, again, if we look at the angle, the triangle, the OPCC to the center of the chord, we've got half the chord distance. That half of that chord distance is the opposite side of I over 2, and we already know the hypotenuse R. And so we've got the opposite side, we can use the sine to get that. So LC over 2, the long chord over 2, half of the chord distance, is equal to R times the sine of I over 2. Multiply the 2 across, and we get that LC is equal to 2R times the sine of I over 2. Substitute in our values, and we've got the long chord as being 419.62 feet, obviously slightly shorter than going along the curve 420 feet. The external distance we can get by looking at the triangle OPI-PC. Now, basically what we've got here is we can get the hypotenuse distance and then subtract off the radius right here to leave us with nothing more than the external distance. The hypotenuse we can get from the fact we know the adjacent side R, and we know the angle here I over 2, and so we have the cosine. So the cosine of I over 2 is equal to R plus E, the distance from O to the middle of the curve, plus the external. So now we just have to rearrange, basically multiply across and divide across. We've got R plus E equals R divided by the cosine of I over 2. When we rearrange, we get the external is equal to R divided by the cosine of I over 2 minus R. I can factor out an R, and 1 over the cosine of I over 2 is equal to the secant of I over 2. And so therefore I can write that the external is equal to R times the quantity secant of I over 2 minus 1. Substitute in our values for the curve, we find out that the external on this curve is only 7.71 feet. And this distance is actually often used in the field when it's possible to check your curves when you're laying them out, because you can measure this distance very easily from the PI to the middle of the curve. So you stake out the middle of the curve from your PC and then check that distance to see if your stationing or if your stakeout is going okay. Now the middle ordinate we can get by looking at the triangle OCPC. Again, we know the distance from the middle of the curve down to O is R. And so all we have to do is subtract off the distance OC from it. Well, if we look at that, we've got R, we've got the I over 2. OC is actually the cosine again of I over 2 times R. And so let me write that down. We've got R minus M, which is OC, divided by R is equal to the cosine of I over 2. Rearrange this again and solve. So basically I've rearranged the thing, multiplied the R across, I've brought then the R across and changed the sign of the entire equation, and I end up with the middle ordinate distance is equal to R minus R times the cosine of I over 2, which is equal to R times the quantity 1 minus the cosine of I over 2. Substitute in my values, and I find out that the middle ordinate distance is 7.69 feet for this curve. Degree of curvature. Again, the degree of curvature is the 100-foot distance laid out. The number of degrees is actually subtended. So basically our degree of curvature is defined by this being a 100-foot arc distance. And what we want to know is what the angle down here is that subtends that 100-foot arc distance. We can get that by a relationship with this, the length, 100 is to D, as an entire circle, 360 degrees is to 2 pi r, which is its circumference. And so there's our relationship. We just take the relationship where 100 feet is the 2 pi r, the circumference distance, as D is the 360. So we've set it up as a ratio. Now we have to simply solve for either D or R here. When we solve for D, we have to rearrange, and we get that 360 degrees times 100 divided by 2 pi r, which yields D is equal to, if we do all the constants here, 360 times 100 divided by 2 pi turns out to be 5,729.58 divided by R. Of course, R is still left there. And so now we have a relationship between the radius of the curve and the degree of curvature of that curve. This is arc definition. For chord definition, we're looking at a 100-foot chord length. So we go back to our long chord formula again, and we know that 100 feet is equal to 2r times the sine of d over 2. Solving for r, basically we get r is equal to 50 divided by the sine of d over 2. So what's the degree of curvature using the arc definition for our example curve? Rather simply, we just put in the 5,729.58 and divide it by our radius, 2864.79. We get that's exactly 2 degrees. For the chord definition, we take the equation we had before, r equals 50 divided by the sine of d over 2, solve it for the sine of d over 2, and then substitute in our r. In this case here, when we do that, we get the degree of curvature is equal to the 2 times the sine inverse of 50 over r, substitute in our r, and we get that the degree of curvature is 2 degrees, 0 minutes, 0.4 seconds. So basically that is our chord definition degree of curvature, and that's how you get it. In summary, the horizontal curve is defined by any 2 components. They can be the intersection angle, the length, the radius, the tangent, the long chord, the external, or the middle ordinate. Typically, it's defined by the radius and intersection angle. This is done by design. When you lay out the tangents, you actually just form the intersection angle. And when you look at safety concerns for the curve, you want to find out how long the curve has to be, you look at the radius. Degree of curvature for arc definition is d equals 5,729.58 divided by r. You can write this also as r equals 5,729.58 divided by d. Or for chord definition, we just have d equals 2 times the sine inverse of 50 divided by r. And that completes this lesson.